Okay. Yeah, okay. So now we need to find what is the bandwidth, right? So it depends, is it a narrow band or is it a wide band? So it will tell from here, D, right? Or beta. If beta is more than 1, then we say it's a wide band, right? So now we apply Carson's rule. So apply Carson's rule here. So we can, well, this D, right? 5.5. This is also beta. This is 5.5. That means it's a wide band, right? So I need to apply Carson's rule, right? So what is Carson's rule? Well, we saw Carson's rule here. This is Carson's rule, right? So 2 times delta F max plus beta. This will give us the answer. So how much will be the bandwidth? If I put in all the values, 100. How much? If I put here delta F max, which is 55, beta is, how much is beta? Well, beta is 5.5. So put that and find out the answer, which would be how much? Is it beta? Is it FM? B, right? It's not beta, sorry, it's FM. This is FM, right? This is FM, right? Carson rule. D, right? We need FM. So FM. FM is 10 kilohertz, right? So put that 55 plus 10 multiplied by 2 is how much? 130. Yeah. 130 kilohertz. Yeah. Yeah. There you go. So you got all the answers. Oh no, one question is left. One question is left. Yes. How much? Okay, sorry. How much is power? How much is power of the modulated signal? E. Power. Remember the formula of power? We did that. It is AC squared divided by 2, right? How much is AC? Is 100 squared divided by 2, right? How much is that? How much is that? 5? Oh, yeah, 5,000 or, yeah, sorry. It is, yeah. And in the exam, never forget to write the unit. If you are not writing the unit, you will get -1. Never, ever forget to write the unit. Yeah, so 5,000 watts or 5 kilowatts, right? There you go. We've done the question. So here is the solution of this question. Here is the solution. We have done already all the questions, right? This is what we do. Power is 5 kilowatts, right? 5 kilowatts, 5,000 watts. Now, next question. A commercial FM radio broadcasting utilizes the frequency band from 88 to 108 megahertz. This is a band for the transmission of voice and music signals. The bandwidth of the information signal is set at 15 kilohertz. This is FM, right? Bandwidth of the signal. This 15 kilohertz is FM. And the peak frequency deviation, maximum peak frequency, right? Delta F max is 75 kilohertz. Calculate the bandwidth of the signal. So now the first question is it a wide band? Is it a narrow band? Right? Then I will be able to calculate the bandwidth, right? The question is find the bandwidth. This is the question, right? Find this bandwidth. But I need to know, is it a wide band? Is it a narrow band frequency modulated signal? Or is it a wide band frequency modulated signal? First of all, I need to answer this. So how can I make sure it is a wide band or narrow band? What should I do? I need to find what is beta, right? I need to find what is beta. Then I can tell, is it this or is it this? So if beta is more than 1, I say it is wide band. If beta is less than 1, I say narrow band, right? So now let's find out beta. How much is beta here? How much is beta? How much is beta? Yes. Beta is? What is the definition of beta? Delta F divided by Fm, right? Yes. Delta F divided by Fm. This is beta, right? Mass. How much is delta F mass? 75, right? 75 divided by Fm is 15, right? So this is 5 or 1. This is much more than 1, right? So that means it is a wideband frequency modulated signal which I need to find the bandwidth. Right? Yes. So I say it is a wideband. It's not a narrowband. The reason is beta. It is more than 1. Yes, then it is wideband. Now I need to find the bandwidth. So what rule I will be using? If it's a wideband, I need to find the bandwidth. Which rule I will be using? Carson rule, right? So yeah, here now use Carson rule. Use Carson rule. Carson rule. Which is what? Bandwidth is equal to 2 times of memorize those, okay? You write for that, memorize those. Memorize all those rules and things. It's very important. So here is the Carson rule. 2 times delta F max. 2 times delta F max plus Fm, right? V means Fm. So apply that. How much is that? Answer is 180? Yes, so it will be 180, right? This will be 180. Yeah. Yes, so this will be 180 kilohertz. Here is the answer. Yeah, so here you see 180 kilohertz. But we use actually what we do instead of 180 kilohertz, we use 200 kilohertz. Well, this is very accurate. 180. We give extra space of 20 kilohertz. The reason is we just want to avoid interference, right? That 20 kilo. Well, normally this is our answer, right? 180 kilohertz. This is our answer. We put 20 kilohertz extra, which is 200 kilohertz. That is what here it says. Separated by 200 kilohertz. Each station is separated by this, right? What is this 20 kilohertz? Remember, this is called guard band, right? Guard band. That means to make sure there is no interference between two stations or two signals, let's say news or movies, we don't want interference, right? So what we do, we put a guard band. Remember a guard band, right? Let's say this is one signal, spectrum of one signal, and this is the spectrum of the other signal. This is music, this is news. So this area, this is guard band. If I don't put guard band, what will happen? They may interference like they interfere like. So this extra 20 is guard band. So they are separated by two. So for example, if I have a channel at 90.1, the other would be at 90.30. Let's say FM channel, if it is 90.1 megahertz, right? The other channel would be 90.3 megahertz, right? So the difference is 200 kilohertz, right? The third station, let's say this is music, this is news, and the third station, the third will be 90.5 megahertz, right? Those 200 is this. I just want to make them separate because if I don't do that, they may interfere with each other. So that's why we put 200 spaces, right? 200 kilohertz spaces. Also, yeah, spaces, and that 20 extra is basically for the broadband. So the stations are now here. So the difference between them is 200 kilohertz, right? That's how the FM stations are. Stations or signals or music and news and blah 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 are like this. This is practical. This is practical. It happened. Okay. So we are done with the done with the, I would say, difficult part. Now, okay, so we have done modulation. Now comes the demodulation, right? We are demodulating the signal. Modulation is done with blah, blah, blah. We vary the frequency. We got FM, we got phase. Now, let's demodulate. So how we can demodulate? We can demodulate by these these methods: frequency discrimination, phase discrimination, and then phase locking. This is probably in the next class we'll do the phase locking. Let's start with the here. Let's start with the first one. But before we go do that, we call a device. It's called band pass limiter. What is that band pass limiter? Is right. So here when we are okay. So I have this signal, right? S of t, that is equal to AC cos of omega ct plus this phase, right? What I need to put t here, right? So if I'm varying the frequency, I call this FM. If I'm varying the phase, I call this phase modulation, right? If I'm varying the amplitude of the carrier, I'm calling it a amplitude modulated signal. When I am doing the amplitude modulation, I have to keep this constant, right? And I have to keep it constant. At one time, I cannot vary 2 or 3. I have to vary just the amplitude. If I'm doing the frequency modulation, I am varying the frequency. I am not varying the amplitude, and I'm not varying the phase, right? At one time, if I am doing frequency modulation, I have to keep this constant. I have to keep the phase constant as well. This is how modulation works. If I am doing phase modulation, I have to keep those two constant. I cannot vary that, right? So this is how modulation is done. Now here, and if you remember, when you are doing frequency modulation, you are not varying FC. FC is fixed. What you are varying? You are varying the frequency deviation, right? You are varying this. You are not varying FC. FC is fixed value. Once it is fixed, you cannot change that. So what you are doing? You are varying delta F. What is delta F? FC, Fi minus FC, right? So you are varying delta F, not FC. So now, what is happening here? When I'm sending a FM signal, right? So keep in mind, I have to keep this constant. I have to keep this constant, right? I am doing FM. What is happening when this signal goes through the channel, right? The channel will introduce noise, right? What happens when it introduces noise? The magnitude, this amplitude, this will start varying, right? This will start varying. Although I have to keep it constant, but I cannot keep it constant. The reason is the noise added by the channel will make this amplitude varying, right? If it is varying, my signal is distorted. So what I need to do, I need to keep it constant. I need to keep this magnitude constant. So when I transmit that signal at the receiver side, I am getting a signal AT cos 2 pi FCT plus this phi, theta. Now this A is having the variation, right? It is no more a constant. It is not a constant, right? It's AT. This is basically the amplitude, which should be constant, but it has variation. It has noise inside it. I need to somehow remove this noise. Before I demodulate, I need to remove this noise. How can I remove this noise, right? So that the magnitude is constant. Because that is what FM is, right? For FM, I have to keep this constant. But channel noise will have variation here. So how can I get rid of this? I need to put what is called a hard limiter. If I put a hard limiter, I will get the signal here at the output of this band pass filter. I will get this 4 pi. 4 pi is constant. Now, hard limiter, how it look like? That's how I function, right? So imagine a cos waveform is passing through this signum function. What will be the output of this? If a cos is passing through this, right? So here we have XL. What is that XL? Here is XL, here is this, right? XL R, XL R. This is basically, it is 1 for R greater than 0, it is minus 1 for R less than 1. That is what XLR is, right? This is what this is, right? So it is positive, right? It is 1 if R is greater than 0. It is minus 1 if R is less than 1, right? Now, what about this XLR here? When a signal is passed through this hard limiter, right? And imagine, keep that in mind, it is a cos. It's a cos, right? So think of that, a cos waveform is passing through this, and this cos is periodic. Cos is periodic, right? This cos is obviously periodic, right? So it is passing through this limiter. What will be the output? Here. And here, I can, well, this is what? This is phi, theta, right? Phase. All this is phase, right? So let's say, okay, so can I write this equation like AC cos of 2 pi FTT plus this phi t? Can I write like this 80? Oh, sorry, this is 80. 80 cos. Can I write this cos of phi I t? Can I write it this way? This is phase, right? So yeah, so just I write it like this form. Now, what is this here? Here, what is my when I pass this signal through this hard limiter? So I want to find what is this XL phi IT. What is that equal? This is my received signal, right? This is my received signal, and this received signal is basically, this is RT, this is my received signal, right? At the demodulator side. So I want to pass it, that signal, which is cos, through this hard limiter, right? Which look like this. So think of that, cos is passing through this limiter. What waveform comes to your mind? There will be a waveform. There will be a waveform. What kind of waveform this will look like? So, okay, so let me make it more simple. I have one, if cos of this phi t, this cos of phi, if this is greater than 1, and I have minus 1, if this cos of phi is less than 1. This is the condition, right? What kind of waveform comes to your mind? If I have that condition, and I'm passing it through here. Imagine a cos periodic waveform is passing through. So what will happen? The top up of the cos and top negative, they will be clipped, right? They will be clipped. So if they are clipped, what kind of waveform you get? If a cos is clipped from up and down, cut up, cut down, and it has this, what waveform comes to your mind? Yes. Cos clip here. Oops. Cos clip here, clip here. Clip means, well, you have this portion, right? So what kind of waveform comes to your mind? A square waveform. Yes, it will be a square waveform. Yes, it will be a square waveform. Right? With what is the period? With t 2 pi. Right? That is the period 2 pi. Now it's a periodic, right? So I can write down the Fourier series of that. It's a square. You just think of that. Cos is passing through this, right? So it will flip the upper, it will flip the down. Upper, down, upper, down. So you will get a square waveform, right? You will get a square waveform. And the Fourier series of what? Essentially it's a periodic waveform. So the Fourier series of that waveform square waveform. And the square waveform I can express by the Fourier transform 4 divided by pi. 4 divided by pi, and it is cos phi I minus 1 by 3 cos 3 phi I plus 1 by 5 phi cos 5 5 cos 5 phi I, and go on, right? So when I pass it, okay, now if I pass this, I have this waveform which is sitting here, which is square waveform. I need to pass it this band pass filter, right? Band pass filter will get rid of all the high frequency terms, right? All of these terms, it will be filtered out, right? It will be filtered out, which means the filter filtered out, filter will get rid of all those terms. So I am left with only this term, right? Now see, here I started with A. I end up, what is this? What is this? This is amplitude, first of all. Is it constant? Right? It's a constant, right? Yes, so it's a constant. Yes. Now see, I started with fluctuation, with variation in the magnitude. When I pass it through the hard limiter, what I got a constant amplitude. So now this is the amplitude, or this amplitude is a constant. So now I am done with the variation of the noise which was introduced by the channel. Right? So what I'm doing here, to remove those noise, to remove the noise introduced by the channel, I need to keep that constant. What I do, I put a signum-like function, well, it's a signum basically, right? When the cos is passing through this signum, you will get a square waveform. Top clip, bottom clip, top clip, bottom clip, and so on. So you get a square waveform, right? That square waveform, what we can express in the Fourier series of the square waveform is this, right? So I have a filter now. That filter will get rid of all those frequencies, high frequencies. It will leave only with this, right? And this is constant now. 4 by pi, it's a constant, right? So I started with A, I end up with 4 pi, 4 by pi, which is constant. Now for me it's easy to demodulate. So here is frequency discriminator. What is frequency discriminator? Sorry, differentiator. You know differentiator, right? So a differentiator, this is the transfer function of the differentiator. If I take the Fourier transform of this, right, inverse Fourier transform of that, this is the frequency domain. If I bring it into the time domain, I take the inverse Fourier transform, it will look like KD, KFD divided d by dt, right? That's what the frequency, that's what a differentiator is, right? The transfer function of the differentiator is this. In the frequency domain, in time domain, it is basically KD d by dt. That's what a differentiator is. D by dt, right? What is KD? This is the constant of the differentiator, right? So now, let's say I have a signal which is FM signal, which is AC cos 2 pi STT plus phi t. This is the signal, FM signal, right? I'm passing it through the differentiator. So that means I have to differentiate this term, right? I have to differentiate this. So here, I put here, I differentiate, I got this, right? So now here, this signal, now this signal is basically AM signal, right? Why it's AM signal? This is the envelope. This portion is the envelope. Yeah, this is envelope, and this is the frequency, right? So now, directly I cannot, for FM signal, I cannot directly demodulate. So what I do, first I convert it into AM, and from AM, I just need to put what? I need to put a, to demodulate, okay, so here is what I'm getting. I modulated the FM signal, right? And then I'm demodulating the FM signal. So first I will convert it into AM signal, right? Because why? Because this is the envelope and this is the frequency. Remember envelope, right? So envelope is my message. So now I need to get back that message signal. envelope, right? Remember that in the AM signal, so we had something like this, right? Something like, and this was the frequency, right? Something like this. So I need to get this. I need to get this. How can I get this? This is now AM, right? So this is that FC, and this is this envelope. This portion. This portion is envelope. So I just need to put an envelope detector, right? If I put an envelope detector, I can get back the signal. So here is that. Right. I put a band pass limiter, right? And then I put a differentiator, which is, we just saw that differentiator. So here is that differentiator. And after that, I just need to put an envelope detector, which will deduct this envelope. This is my mapping signal. I'll use that as my mapping signal. Right? So here, this is envelope detector, right? This is the envelope detector output. And here you see here this signal d phi by dt, right? So now if I put in here that d phi, what is phi for AM signal? Phi for AM signal is, remember this thing, theta or phi for AM signal. Remember that integrated form, right? Phase, right? Phase of AM signal. It was that integrator, right? This thing, right? Yeah. So again, you don't need to normalize this signal. You don't need to. This is normalized. Okay, fine. Same thing. You don't need to normalize. So plug in there. If you plug in there, you will get, try to solve it. You see here, that output YD here, I have my message signal here, right? So that means I got back my message signal. So what I did, there are 3 steps I'm doing. The first step is I am first applying, okay, here I have a band, but this is my XF FM signal. I pass it through the band pass limiter, then the differentiator, and then I put an envelope detector. Why I am putting an envelope detector? The reason is I cannot directly get FM demodulated. I have to convert it into AM signal. So I converted it into AM signal. AM signal detection is possible with the envelope detector. So that's why you see envelope detector, although it's AM, right? So that's why envelope detector. So we got our signal back. This is called the frequency discriminator, right? So here is that frequency discriminator. How we get it through band pass limiter. So here is the band pass limiter, right? I need to put that band pass limiter. The reason is I need to remove the noise variation before I demodulate. So here first I remove that noise. I got a waveform. I pass it through the differentiator, and after differentiator I got a signal which look like this, right? This is the envelope. I need to get this thing. If I need to get this thing, I need to put an envelope. Remember what does an envelope detector look like? Envelope detector look like? Remember? It consists of a diode, a resistor, and capacitor, right? Remember? Envelope detector consists of a diode, a resistor, and a capacitor, right? Okay, I'll show you. Okay, so let's move forward. Here is that envelope detector, right? Diode, resistor, capacitor. So, okay, now here is slope detector. What is slope detector? This is basically slope detector. Well, this is the equation for that slope detector. Here, if you notice here, well, this is the transfer function of the slope detector. So, you see, it's a slope, right? So, if I'm moving in this direction, I have this FC in the center, and then FC plus what we are using this equation, FC plus VT is transmission, right? So, if I'm moving in this direction, up in this, if I'm here, I'm here, I'm here. If I'm moving in this direction, right? Right? If I'm moving in this direction, means if I'm increasing frequency, the magnitude is increasing, right? If I'm moving in this direction, the amplitude is decreasing, right? This is slope. So let's find out here better. So now I have this slope deductor. It's a single tune circuit. Right. So remember tune circuit in your which course did you do tune circuit? Oh, sit down. Where is Tony? Where is Tony? Tony, what is his name? Tony? I don't see him. There's one student. Tony? I don't see him. Oh, yeah. Who is your friend? Kunal? Your friend? I don't see him anymore. Last time he was your friend. I don't know now he's your friend or not. There was one student. Do you remember? Do you remember? Anyone remember Tony? Do you remember Tony or? There was. Who was your friend? Kunal, who was your friend? Oh well. Okay, I'll remind. I'll remind his name. Who? Sorry, Peter. Yeah. Tony. But trust me. Up till now I call him Tony. Yeah. I don't see him. Where is he? Oh, who is the class monitor for his class? Who is the class monitor for his class? Oh, fine. You? Do you see Peter? Where is Peter? Where is my shit? Okay, so the question is, I have my USB and I don't find my USB. Oh, here. Okay, so Ray, can you help me with the file here? So I go to here and quiz. Okay, so we didn't do quiz 3, right? We have 2 quizzes up till now. Oops, yeah. So this is quiz 3 here. So can I make it bigger? Can I make it more bigger? More bigger? Can you see it? No? No? How would I make it bigger? Ray, can you help me make it a little bit bigger? No? Oh, well, try to see it. I think no. A little bit better, right? Little bit better. Problem is, I'm trying to make it bigger, but for some reason it's not getting bigger. It's not getting bigger. So I can try from here. No. Try more. No, can't. Sorry. Now, probably. can you collect from that side? And Ray, can you collect from this side? The quizzes. Give it to Scott. Give it to Scott. Scott? Thank you, Scott. Thank you. Thanks. Yes.
I want to ask about the exam will also provide a formula sheet.
No.
No formula sheet.
You have to memorize those. Well, there are not too many formulas. There are very few formulas.
And the exam will only contain chapter 4 and 5 exam. No MATLAB or some
No.
spectrum.
You need to draw the spectrum.